All right, welcome back to the spring semester, and this is our first seminar, machine learning seminar. It's my great pleasure to introduce my new colleague, Liyan Xie from Department of Industry and System Engineering. I think Liyan joined in the fall, right? Or last fall, yes. So very new. Liyan was a senior professor in Chinese University of Hong Kong before he joined us, and she got a PhD degree from ISV Department of Georgia Tech, and her research interest is an intersection of statistics, optimization, and machine learning, especially topics like sequential decision making, diffusion models, and spatial temporal data analysis, and other applications. So I think Liyan is going to tell us more about how to do transfer learning for diffusion models. Let's welcome Liyan.
Thank you.
It will be better is because United is doing recording. You can via this one.
Yeah, okay. Thank you, Ju, for the kind invitation and also introduction. And I'm very glad to be here. And also, I want to say Happy Chinese New Year, since I'm glad to be here as a speaker today. And today actually also happened to be the Chinese New Year Eve. So today I'm going to talk a little bit about a recent work on transfer learning for diffusion models. So this is a joint work with my former student and a few other co-authors. So first of all, I want to introduce a little bit about the overall background of the overall transfer learning framework. So in traditional machine learning, usually when we're given a batch of data, and then we can choose to train, for example, to train a machine learning model given this data. And however, in a lot of cases, usually what we also cares about is how to do this kind of machine learning model on how to perform certain tasks on a target domain. And usually the target domain distribution can be slightly different from the source domain distribution, although that typically also share certain similarity with each other so that we can transfer the knowledge. So the traditional machine learning will choose to do and that will choose to train the machine learning model again using only the data from the target domain. However, the transfer learning framework actually, the overall objective is to try to transfer the knowledge that we have already learned in this kind of existing machine learning model and combine this learned knowledge together with the data from the target domain and then try to build a new machine learning model, usually through some kind of fine-tuning or update. And in this way, it can usually be able to achieve a pretty useful new machine learning model, pretty effective model using usually a limited amount of data from the target domain, because it is usually the case that we have many more data from the source domain as compared to the very limited data from the target domain. And this kind of transfer learning framework has a lot of real applications as well, including but not limited to, for example, recommendation systems, speech and image recognition, and also natural language processing, where you can learn the previous model in some source domain with certain language and then try to transfer the knowledge to some target domain with a different language system, and also self-driving car as well. So what I want to talk about today is still inside this overall transfer learning framework, but we're going to focus on a very specific task, which is we want to be able to learn a diffusion model, which is one of the most popular and commonly used generative model nowadays. So in the transfer learning framework, we are going to assume that we already have a pre-trained effective diffusion model from using data from the source domain, where we assume that we do have a lot of data. And then we now also have a limited amount of data from the target domain. And we want to be able to use the original pre-trained diffusion model together with the limited data from the target domain. And actually, in our framework, we will also use a little bit of the source data as well, and combine them together to try to build a new diffusion model. So this is a task. And so in today's talk, I'm going to introduce our proposed method, which is basically a fine-tuning free framework for transferring this pre-trained diffusion model from the source to the target data. And I will also introduce briefly one possible extension. That is, we can also choose to include and have this framework work for the case that you actually have the labeled data as well. And in that case, we can extend this proposed methodology to the conditional version for diffusion model and in order to model the joint distribution of the data or the conditional distribution of the data condition on the labels. So this is the outline. So I plan to give a brief introduction to diffusion model, particularly for the scout matching part, which will also build the foundation for the main insights of our proposed algorithm. And then I will introduce the proposed algorithm, which is basically based on a density ratio inspired guidance term. And that will introduce how we actually build a guidance network to try to learn this guidance term. And that will also introduce like two additional regularization terms that we found very helpful in practice in terms of the improved performance. So first of all, diffusion model actually emerged as a very commonly used general model nowadays. And in the very early stage, we have GAN and VE and also flow matching kind of general model. But recently, we do have, like, for example, diffusion model like stable diffusion, where we have this UNet serves as a very fundamental neural network architecture. And we also have, for example, the large language models, ChatGPT and DeepSeek recently. And but the key feature of all those deep generative models are that usually tends to have a lot of parameters in their network architecture, which basically means that it's very difficult for us to retrain this diffusion model if we only have a very limited amount of target data. And the diffusion model emerged as a very powerful tool recently during the past 3 or 4 years. And so what diffusion model do is they're going to do the generation of, for example, taking image data as a particular instance. Diffusion model will take the noise, actually it's high dimensional noise as input, and through a sequence of transformation to be able to eventually generate a high quality data. And in each step of this, within this sequential transformation, each step of each of this so-called backward process can be performed through learning like a deep neural network. And it serves as a backbone of, for example, image generation, video generation, like a lot of commonly seen tools nowadays. And if we compare diffusion model with the traditional type of general models, such as GAN or VE, the key advantage of using diffusion model, which is also one of the motivation that why we care about learning the diffusion model under this transfer learning framework. So diffusion model is able to generate high quality data through this high D to high D sequential transformation, and the training as compared to GAN is usually more stable, and the performance is usually more flexible and accurate, although the training speed is indeed slower compared with the previous methods. And it is also commonly used in a lot of application domains as well, such as video generation, this protein structure design, and in some of this reinforcement learning and control problems. And it has already seen a lot of success in, for example, the ImageNet benchmark, some of the stable diffusion community, and this protein design. So overall, I just want to say that one of the main reasons that we want to learn about the transfer learning ability and how to do that under the diffusion model framework is because the diffusion model has emerged as a widely used and very powerful tool nowadays. And so then we started to think about how to really leverage the power of and try to unleash the potential of diffusion models if we only have limited amount of data in the target domain. So in the next few slides, I will just briefly go through the detailed generation procedure. And the reason I want to go through this is because through this procedure, I will also introduce the skull function, the skull estimation part. And that actually serves as a fundamental part when I introduce why we, all the insights of our proposed algorithm. So diffusion model generates a sample from noise. So we have the high dimensional noise as input, and then through a sequence of transformations to eventually be able to generate the high quality image. So the forward process, for simplicity, if we describe the forward process in discrete time, then it can actually be written as like adding. We just continue to add Gaussian noise into the original data. So we have the original data x0, which is our real data, and then we're going to continually adding Gaussian noise until in the very end we're going to have a crafted image, which roughly follow, for example, standard Gaussian distribution, which we call the approximate noise. And since it is in discrete time, so when you have a finite time, so usually this is just approximately standard Gaussian, not exactly Gaussian. And so what is really interesting is the backward process. So because the forward process can be viewed as some known information. So I can control what kind of noise corruption framework that I want to add. And so what I really need to learn is reverse process, which is also called the backward process. So in the backward process, my input will actually become some image from the standard Gaussian, which is actually the noise distribution. And then so in the diffusion model, people will try to learn this backward transition using a neural network to try to approximate the actual backward conditional probability here. And actually, I think it might also be simpler to write everything in continuous time as well. And this is also what we used in our transfer learning framework. So if we model everything using like a stochastic differential equation in continuous time, then this is how it looks like. So in the forward process, we again add Gaussian noise, and that can be represented as a forward stochastic differential equation. So and this dxt actually shows you in which direction I'm going to add noise to my current observation xt based on this drift term and also this noise term, all this variance term here, where capital Wt is Brownian motion. And we know that we do have a closed form expression for the backward process. So we have this forward and backward coupling for this stochastic differential equation. So if we use this as our forward process, then this will become the backward stochastic differential equation, meaning that if I use this as my forward process to generate a bunch of trajectories and to have the path measure for my trajectory, then I can actually regenerate all the same path measure for my entire trajectory using this backward stochastic differential equation as well. And what is really interesting is in the backward process, especially in the drift term, in the backward process, we have a skull function here. The skull function actually kind of can be treated as some additional like drift term that we have as compared to the forward process. And it is defined as a gradient of the log marginal distribution time t of your observation xt. So our main insights for our proposed transfer learning algorithm also comes from some observation that we observe for the skull function between the source and target domain. And so this is how people usually do to learn that skull function. So I forgot to mention that. So although we know the closed form expression for the backward stochastic differential equation, but usually you cannot directly utilize this because the path measure of this marginal distribution PT and also the skull function here is completely unknown. Because this PT actually is a convolution of your original data distribution Tx0. And the and this transition, which is usually a Gaussian transition kernel. So, but since we do not know what is our original data distribution, so this PT is also unknown, and it is something that we need to learn in order to be able to finally apply this backward process. So in order to learn this backward process are essentially captured by this skull function, the gradient of log of your marginal data density PT here. We can use this so-called skull matching objective. So we have our skull network here. We can use a neural network to model the skull function, this S, usually as theta, where theta can denote the network parameter. So we have S, X, T, and you also have the time as one of the input, because the skull function in this case is time dependent, because your PT actually depends on the time. So this is usually our training objective. So we're going to train this skull network by trying to minimize the least square error between the learned skull network and the true skull function. So although the true skull function is unknown, but we have some equivalent denoising skull matching objective, so that eventually when we're trying to evaluate or train the objective function, we actually do not need access to the true skull function. But this is the overall idea. So we aim to learn a skull network that can hopefully approximate the actual skull function, which is unknown. So given this, after introducing this skull function idea and also the training of the skull network, so I think we're ready to jump into like the main insights of the transfer learning algorithm that we want to study. Recall that we're under this transfer learning framework. So we do have a lot of data from the source distribution here. And meanwhile, we also have usually a limited amount of data from the target distribution. And so for the source data distribution, I can, as I mentioned before, if we want to be able to train a diffusion model, it involves both the forward process and the backward process. So we can have a forward process by continually adding Gaussian noise to the original data. And so we can do the same thing for our targeted distribution as well. So, and suppose that we're going to adopt exactly the same noise injection process. So I'm going to add exactly the same Gaussian noise, and that actually translates to the transition probability for my source data parse measure and my target data distribution equal to each other, meaning that, so although the x is 0, the distribution of my x0 differs because one is from the source data distribution and one is from the target data distribution. But I will assume that we're going to add the same Gaussian noise, and then so that we can have the same transition probability for both the source and the target. So under this condition, if we look at what will be the actual backward process, because we're going to use that backward process for generation. So for the source data distribution, the backward process will also be a stochastic differential equation, and we have a term here which actually represents the skull function, but that is under the marginal distribution under the source distribution. So all this PT, the marginal distribution at time t, they're being obtained by adding Gaussian noise to my source distribution data, and then obtain the marginal distribution at time t, and then take the gradient of the log. Oh, sorry, I forgot the logarithm here. But this is just the skull function of the under the source distribution. And similarly, if we look at what will be the generation process for the under the target distribution, then we will also have a target skull function here. So again, sorry, I forgot the logarithm here, but there should be a log, and this will be the target skull will be the skull function under the target distribution. And this, so I will always use P to denote anything related to the source distribution, and using Q to denote the distribution related to the target. And so the key insights behind our algorithm is this observation. So our key observation is that we will be able to link. So sorry again, we need to have a logarithm here for both of the scale function. And but the key observation is these two scale function, the scale function on the source and the scale function on the target domain at the time index t, the scale of their marginal distribution actually can be linked to each other. They are actually related to each other. And the difference between these two scale function is actually this term. And this term is related to the density ratio between the source and the target domain. And so this term actually measures the gradient to xt, the logarithm of the expectation under the posterior distribution px0 conditional xt, and then the density ratio between q and p here. So we have we have a formal theorem to explicitly characterize this relationship between the pre-trained scale model and the target scale model, which is what we desired if we want to be able to perform the generation task. So the theorem basically says that let's consider two diffusion models on the source and target domain, denoted as P and Q, which is exactly as shown here. We have the forward and backward process on P. We also have the forward and backward process on the target domain. And we assume that the forward process they're actually identical between the source and the target domain, which basically means that we have the forward transition probability to be identical to each other, although we have different initial distribution. So given that, we actually have the scale estimation on the optimal scale estimator in the target domain. So this actually just represents the actual scale function on the target domain. Can be written as the actual scale function on the source domain plus some additional guidance term. So actually, this is the main idea behind this talk, and all the following part will just be about how to really implement this and how to approximate this term, and then incorporate this term into the generation process. But this is a main idea. So we have this term, and we call the guidance term. And so if we're able to really compute and approximate this guidance term, and then that means in the backward generation process, we can leverage this pre-trained scale model that we already have, and then add this guidance term into the scale function, and then using some like DPM solver to simulate that backward process and to generate sample for the target domain. So that is a main idea. And the main idea is here we kind of derive this exact formula for this guidance term, which exactly equals to what will be the difference between the source, between the scale function under the target and the source domain. Okay.
A quick question there. So the randomness in the second term, the guidance term, is because the x0 is actually the one predicted by the current xt, or?
Yeah, this x0 is predicted by the current xt. So
this x0 is not the original training x0, that means, right?
Yeah, it is not the original training.
Oh, I see. Yeah.
Yeah, it is not.
I got a little bit confused because I thought x0 is in the training set is actually a deterministic quantity, so why there's an expectation, but yeah, okay.
Yeah, right. So because this P itself can be roughly viewed as a path measure on like the entire path from time 0 to time 1, or from time 0 to time capital T, and with x0 to be generated from the source distribution, some px0, and then we add the Gaussian noise.
Yeah, but this is a predicted x0.
Yeah, this is
not a true x0.
Yeah, this is a predicted x0, so which is condition on.
If you put like a hat or something, you know.
Yeah, thank you for the suggestion. But actually, in practice, when we're trying to approximate this term, actually what we do is something like Monte Carlo simulation. So we also choose data from the training data and then do some, and then add the Gaussian noise perturbation. But in principle, this doesn't need to be the original training data. It's actually something that we can, basically the posterior distribution that learned by the source diffusion model. Yeah. Okay, so and I'm going to talk a little bit about how we actually approximate this guidance term so that we will be able to compute exactly the quantity of the guidance term using a guidance network. So the key idea here is we want to be able to learn a guidance network we denote as this H function, which also depends on the current value and also the time index. And we hope that this guidance network can be able to approximate the expectation of Px0 condition xt of the density ratio between the target and the source domain. So the reason that we want to be able to learn this guidance network is because if we are able to find a network that can approximate this quantity, then by taking the logarithm of this quantity and then taking the derivative, we will be able to obtain the value of this guidance term. So in order to learn this guidance network, we have two steps. In the first step, we actually train a binary classifier to approximate the density ratio here. And in the second step, we so given some estimated density ratio, then we use Monte Carlo simulation to estimate this entire this expectation quantity. So in the first step here, it's just we just adopt a very simple binary classifier trying to approximate the density ratio, but I believe there can be like more involved and well-designed and some refined technique in order to improve the efficiency. So recall that we have the source data and target data, so that can be viewed as two class, and then we just learn like a neural network as a binary classifier, which takes any of this image as input and then output like a value between 0 to 1, and that value represents how likely we're going to classify this image as belonging to the source domain. And we adopt the very commonly used logistic loss function. And so if we do train everything to optimal, then eventually the output of this classifier, this binary classifier network, the ratio of 1 minus output divided by the output will be approximately the density ratio between the target and source domain. So given this estimation for the ratio using some binary classification type of algorithm, then we use the Monte Carlo simulation to start estimating this entire expectation term. So actually one of the key difficulty in estimating this expectation is we actually do not know what is the posterior probability. So actually we do not know what is Px0 condition on xt. Because that actually corresponds to the ground truth backward process. So given the current xt, which is some corrupted image, then what will be the probability for the original x0? So the key difficulty actually lies in we have no knowledge about Px0 condition on xt. And then we realize that actually in practice, we do not need to estimate this conditional probability, but instead, what we really need is just the joint distribution, or if you can sample from the joint distribution of x0 and xt. So this is a key observation. The second observation that we have is, so if we define the objective, so suppose that we want to be able to find the optimal guidance network parameter, this psi star, such that the guidance network, the output of the guidance network can be approximately equal to this expectation term. Then we realize that this actually can be the objective that we can utilize in practice. So our key observation is if we choose this objective function as our learning objective, then its minimizer, its minimizer in terms of the population loss will actually satisfy exactly what we need. And the key advantage of using this objective as compared to directly trying to find the unknown posterior probability and then try to take some average and to approximate this. So the key advantage is here. What we only need is a joint distribution if you are able to sample from the joint distribution of your x0 and xt. And this is actually doable because I can randomly sample my x0 from my training data from the source domain and then add the Gaussian noise corruption to it to obtain the xt. So this is a key advantage. So by showing these results, we kind of avoid estimating this desired term by trying to find something to approximate the posterior distribution and convert it to some learnable objective or some objective that is able to be approximated using the sample average by sampling the pair of x0 and xt from their joint distribution. And we show that if we use this as an objective, then the optimal solution exactly equals to what we want here. So given this, this actually summarizes the vanilla version of our learning process for the guidance network. So the key ingredient here is we model the guidance network as a neural network, this H function here that depends on the observation value and also the time index. And so this actually is supposed to be the density ratio, but since we do not know that, and then we build a binary classifier to learn the density to obtain the density ratio estimate. And for the sample average approximation process, what we only need is we only need to jointly sample x0 and xt from P, and this can be achieved by sample x0 from the source data domain from the source data, and then obtain xt or sample xt by applying this forward transition, which is just a Gaussian noise injection process. Okay, so that is actually already the main idea of the proposed algorithm. And in the remaining, I also want to briefly introduce like two additional regularization terms that we found is pretty helpful in practice empirically to improve the performance. So the first regularization term in the objective function that we utilize is the so-called, which we call the cycle regularization. So the main idea behind designing this additional term in the objective function is because first of all, recall that in the very simple version of the training of the guidance network, actually we didn't use any. So during the training process of guidance network, we didn't use any data from the target domain. So all the data from the target domain that were only used when we're trying to do a density ratio estimate at this very first step. But during the entire training of the guidance network in this version, we only sample data from the source domain distribution. So that is why that actually motivates us to think about whether it is also possible to try to incorporate, even if we only have limited data from the target domain, whether it is possible to incorporate some of the limited data in the target domain, and whether that will be helpful in improving the overall performance of that guidance network. And then we realized that since what we want to do is find a guidance network that can approximate this expectation term. And currently, this expectation term is only written using data from the source. And then we realize we do have some equivalent formula for this expectation as well. Or in other words, we also have some expectation, but this expectation will be under the target domain. And this expectation exactly equal to this one. And that actually means it will be possible for us to try to incorporate some of the data from the target domain into the learning process as well. And so that actually means eventually we realize that if we want this optimal guidance network to be approximately this expectation term, then it should also be the minimizer of this objective function. And this objective function can be directly evaluated using data jointly sampled from the target domain. So again, although we have something like the posterior probability under the target domain, but eventually the objective that we can use doesn't rely on this. Instead, we only need to be able to sample data from the target domain distribution Q to have the joint sample X0 and XT. And for this term, so this QT and PT is actually represent the density ratio at time t for the marginal distribution QT on the target and the marginal distribution PT on the source. And this actually means we will need to be able to build some like a multiple binary classifiers, one at different each one for a different time index, and then eventually to approximate this ratio. So it will be a little bit more computational effort. So this objective that can be evaluated using the sample average approximation by drawing samples jointly from the target data distribution. And in addition to this term, we also have one last regularization term, which we call the consistency regularization. So the key idea behind this is, first of all, since eventually our ultimate goal is to be able to adding this guidance term such that the resulted updated score function can equal to the true score function under the target domain. So that basically means our ultimate goal is we hope by adding this guidance, the resulted score function can indeed recover the score in the target domain. So given this, then that actually motivates us to consider some additional regularization term, which is we hope this guidance network optimization can also be a solution or can also be a minimizer of the score matching objective under the target domain. And in order to be able to evaluate this objective, what we only need is also just the joint sample from X0 and XT under the target domain. So, given that, we do have some revised algorithm by incorporating these two additional regularization term. So it's a bit heavy here, but I'm going to point to you the most important part. So the first step will be we will jointly sample X0 and XT from the source domain, and then using our original, which is also the main objective function that we're going to use since we have a lot of data from the source domain. And so this is one of the key components in our final loss function. But meanwhile, these two enhancements about these two additional regularization term, what we're going to do is we're also going to use some sample from the target domain as well. And using this sample from the target domain to compute these two additional regularization term, and then eventually combine these three terms together as a weighted summation with some tuning parameters, and then eventually optimize over this objective function to learn the optimal guidance network. And lastly, I also want to briefly mention this extension to the conditional diffusion as well. So as compared with the unconditional version, in the conditional version, we're going to have the labels attached. We're going to have the corresponding label for the training data in the source and target domain. And our observation under this conditional version is, in other words, this Y actually denote the label for each of the data point. So our observation from the previous, our insights from the previous unconditional case, that can be easily extended to the conditional version by adding this label into the calculation of the score function. And we still have the score function under, or the optimal score function under the target domain should equal to the summation of two components. And the first component is just the pre-trained conditional model on the source domain, which we assume that we know. So in the transfer learning framework, we assume that we have perfect knowledge about some given pre-trained model. And for the second part, so the second part actually represents the conditional version of the previous guidance term. So this is a skull network, actually the conditional skull network on target domain. And this is a conditional skull network on the source domain. And then we also have this additional guidance term, which we call the conditional guidance as compared to the previous unconditional version. And this can be, again, approximated by a guidance network. So lastly, I also want to briefly mention two numerical examples. The first example is a simulation example where we adopt a very simple like a proof of concept example using Gaussian mixture distribution. So this is our source, a Gaussian mixture with two components. And this is our target distribution, a Gaussian mixture with also two components, but the mean actually differs from the source. And we tried this using a lot of data from the source domain and then using different number of samples from the target domain, ranging from like only 10 samples from the target, 100 samples and 1,000 samples from the target domain. And we compared with the vanilla diffusion, which is we just train a vanilla diffusion model using data only from the target domain. And then some fine-tuning diffusion approach. And so this transfer-guided diffusion model refer to our proposed method. Since in this example, we do know what is a ground truth density function, so we also evaluate the average likelihood function and compare the average likelihood of the proposed method to this to baseline method. And our method do achieve a relatively higher average likelihood. And we also perform the experiment using a real ECG data set as well. So what we use as a source data is a relatively bigger ECG data set that contains over 20,000 ECG sequences. And what we use as a target data is a relatively like smaller data set. And then we compared this is like the feature map, which is a TSNE of the generated data. And quantitatively, we also compare these two metrics, the diversity metric, which is bigger the better, and also the FID, which is smaller the better. And so overall, our method do achieve relatively good performance as compared to the other two baseline methods. And we also have a comparison on the baseline on the downstream task, which is a classification task, because for both of these two ECG data set, we do have the label for each ECG sequence. So overall, we compare the area under the curve and some of the other recall and precision measures, and the proposed measures still achieve these two simple baseline that we compare with. Okay, so finally, I just want to briefly mention a comparison to literature. So in the existing literature, the transfer learning for diffusion model that can usually be performed using this fine-tuning approach. So this fine-tuning approach basically means that we can either choose to fine-tune like a small set of the parameters, or we can choose to fine-tune with some additional penalty term. And we also have some, for example, text-to-image diffusion model and also human feedback, which is similar to the alignment where you have a reward function that you are trying to modify the generation process to align with that targeted reward. And there are also some like non-diffusion general models. So my personal feeling of the comparison between this density ratio inspired transfer learning framework as compared to the fine-tuning type of method is, first of all, we are kind of fine-tuning free. That basically means we do not need to think about which subset of the parameter that we need to fine-tune. Or we do not need to, for example, perform some preliminary process of trying to find which is the most effective subset of parameters to fine-tune. And a quick summary here. So we introduce a fine-tuning free framework for transferring a pre-trained diffusion model knowledge from the source domain to the target domain. And it is also possible to extend to some conditional version. And we also have some future work going on, like the validation on more and more diverse tasks. Okay, so that basically concludes my talk, and happy Chinese New Year, and then we'll be happy to take any questions. And also my office is in Linda Hall, and you can also send me an email if you want to discuss anything related to this. Thank you.
Thank you very much. Any questions?
I have a question. So this is a really good work. So I'm curious to, have you tried to test the model on some image data set, like transfer from like some kind of human face to another kind of human face, or like from one data set to another?
Yeah, so what we're doing now is we're actually testing this on some like text to image task, but that's some ongoing work. So I do not have much results to share this time. But one of the main reasons that I mainly show this ECG data example is because actually this represents a case, for example, in some biomedical engineering or some healthcare related cases. We do have some data from the target domain, but usually you have very limited amount of data. And I think that represents a very unique case as compared to, for example, the image case of some other cases. Because in those cases, if we do have a relatively larger amount of data on the target domain, then the fine-tuning method that can also work pretty well in terms of many like different perspectives. But if we do have our limited data on the target domain, although we didn't do that theoretical analysis, but as being shown in the numerical results, I do believe that the performance of training like a classifier to do that density ratio estimation tends to be like more accurate. Although it can usually cannot exactly estimate the magnitude of that density ratio value, but the landscape has been recovered pretty well. So, and that usually is enough in terms of the guidance part. So I believe the sample complexity of training that density ratio part as compared with like you directly training or fine tuning a diffusion model in this kind of larger scale on the target domain, that kind of differs between different applications. So in some applications, we do have limited data, but in some others, we if we have more data, then we do have more maybe better options on that part. Yeah, but we do have that ongoing, but yeah.
Thanks.
You had a question. What was that one that was audio to portrait or something? Is that something you're working with or something? It showed a face and it said audio to portrait.
Audio.
Yeah, audio.
This one? You mean this one?
Well, you had one where there was some picture of a face, but you're not working with audio there.
Yeah,
right there.
I'm not working
That's
with
right.
audio.
Down right up the top there at the top.
This one?
It says and a portrait, yeah, audio driven synthesis.
No, I am not working on that.
Oh,
I'm
okay.
just using this as some of
Awesome.
the evidence showing the success of like
I'll
diffusion
look
models.
that one up.
Yeah, but I'm not working on audio. But transfer learning can be applied from that audio kind of transferring knowledge.
Gotcha.
So does your method assume that the source distribution and target distribution at least the data, they need to share the same ambient dimension, right?
Yeah, they need to share certain.
Well, at least they should be the same data type. Either they are both ECG data, or they are both two Gaussian mixture, or they are both image.
Yeah, right. So if you do have like different, different, for example, embedding space or different kind of types, then you do need a little bit more effort. For example, you can build some like optimal transport map to try to align all the features on the data you have in the target domain and align that with the source domain. So we do have some example that especially when dealing with that labeled data case, we do have the example that the label set we have for the source data actually differs from the label set we have under the target domain. And but in that case, the feature actually that still shares certain similarity. But in that case, actually, what we're trying to do is build some optimal transport map to so that you can better map all this unseen information to the information that you have already seen.
Yeah, thank you for the answer. I think this talk is very, very inspiring. And I have a follow-up question. So do we actually need to assume the source and target distribution, they are close to a certain extent? Like
Yeah.
since sure the two mixture of Gaussian, right? Like those are that is a toy example, but
Yes.
the distribution there essentially need to be very similar. I
Yeah.
also mentioned optimal transport is essentially want to find like the shortest distance between like
Yeah.
two distribution.
Yeah, right.
So
Yeah,
is there
that
any
is-
assumption that need to be satisfied in order for this transfer learning framework?
Yeah, that is a very good question. So although we didn't have like a concrete formulation in terms of that assumption, but I think the general idea to be able to transfer knowledge is they do share certain similarity. And in our case, actually, this can be showing in this density ratio part as well. So if you do have two distributions that is very far away from each other, then that means estimating the ratio can also be challenging. Although there was some recent work that uses so-called like a telescope and density ratio estimation, like you can build some intermediate density so that the neighboring one are closer to each other, and then can using like the chain, like the production of all the estimated ratio to try to improve the performance. But the overall idea is if we do have P and Q to be super far from each other, then that will definitely cause some difficulty in terms of the estimation part, which means learning the guidance can be very difficult. So yes, the overall assumption of this work and the overall test case that we use that indeed assume that we do have certain similarity and they're not too far away from each other.
Yeah, and that actually brought up another question that you also mentioned. So it's one thing that the two distribution need to share some similarity, but also these two distribution, they essentially have different data about volume. For the target distribution, we only have a small data set. So in a small data set, if probably like even with Monte Carlo sampling, it's probably still challenged to have a good estimate of the density function for the target distribution. So is there also, do you have an ablation study like so basically what that means, so we still need to have like a decent amount of the target data set in order for
as you were saying. So I think so, and we do have some ablation study. We have two type of ablation study. The first is we have the three components in the objective function, and we have the ablation study of removing like two of them and see what happens. And we also have the ablation study regarding the density ratio part. So in that Gaussian mixture example, we do try to visualize what will be the estimated ratio value, even if we only have like 10 samples in the target domain. And but I think 10 samples for that case can still be considered as relatively large in that case, since the number of parameters small. But we do observe that like even with 10 samples, although the resulted estimated value doesn't exactly match with the true density ratio value, but the landscape has been recovered pretty well. So which means the relative value of different locations has been recovered pretty well. But yeah, so it is indeed the open question to start as a future work, like how to further improve this.
Thank you for the answer, because I think the Gaussian mixture is two-dimensional, right?
Yeah.
But when you move to high dimensional, like image data set, like it's even more challenge to estimate a good density function.
And also
only some data.
It's also challenging to like visualize and to know whether this is accurate or not, because you have no ground truth. So all you have is just using some like evaluation. Although I think there's no like universal evaluation framework for a lot of different tasks, but yeah.
Okay, thank you.
Other questions?
Maybe I have a question. So I'm also curious about the two distributions, I mean, source and target. I had add one point, because in practice, I mean, when we add in the noise, right, it's not infinite. So there, I found there's some paper talk about the gap. I mean, so that is for even for, I mean, two very
Yeah.
close distribution. When we add the noise, it's not totally Gaussian. So we can see some patterns there. So yeah, especially for some high dimension data, I suppose, I mean, two distribution actually are not, I mean, there's some gap. So
Yes,
yeah.
exactly. So if we're using just a finite step of adding the noise, then exactly. So eventually we only have an approximate noise. But in the backward process, we are starting with exact noise, which is standard Gaussian. So there will be indeed be a gap here. Yeah, but that will be interesting to study like how exactly that amount of difference affected this. But in this work, we are actually not starting that. We're just treating that we have like because we didn't kind of focus on what will be the theoretical guarantee for the transfer learning perspective. We're kind of starting from the insights, assuming that we have a perfect knowledge on the skull function and then how the difference behaves and how to approximate that difference. But this is a very good point. So I guess that will be more related to some of the theory part of diffusion model and see how that difference actually propagate and affect the generation.
Yeah, I saw some paper, they want to try to, I mean, smaller the gap between the two distributions. Yes. Yeah, very good talk. Thank you very much.
Thank you.
So I have a question about this. Obviously, people are gradually moving to flow matching, right? So, do you think it's better to actually, think about transfer learning for flow matching framework rather than diffusion models? Because if you think about the demand in diffusion models, we are looking at skull functions, which may have a lot of problem, because not all distribution have density function itself, and also, even if have density function doesn't mean they're not differentiable, right?
Yes.
So they have a lot of problems, The reason I think about this is, because we are dealing with the images most of the time in micro. It's hard to say they actually have density.
Yeah.
Even, right?
And sometimes when you have categorical data,
Yeah,
it's also
exactly. So flow matching, is much more attractive to me, in that sense, because you don't need to deal with skull function. That's much more attractive. So do you think this kind of idea can be adapted for flow matching framework?
Well, that's a very good point, but to be honest, I don't know. So I think for the flow match, it's more like the ordinary differential equation perspective. So you have a drift term there.
Right.
But this part, the skull function also appears in the drift term. So we kind of adding some guidance to that term to try to shift the gear and let the general sample to be followed from target. I'm not sure. I will think about it. I think maybe it is possible to kind of study what will be or what might be the theoretical difference between the
Yeah.
the two drift terms in that ODE part and
I
so.
feel like it might be easier. It might be easier because I think that the entire challenge here is about expectation of the density ratio, right? So they're probably
there's more
I
deterministic.
don't know. Maybe there's no expectation term or something. I mean, I would imagine there's still some kind of density ratio, right? But maybe it's not this complicated.
Yeah, right. I think their density ratio is more
Because
easier.
the density will be induced by the velocity field in flow matching context. So that means probably you need to compare you need to slightly adjust the
velocity field to
Yes.
that direction.
That might be easy.
I see, but that amount of adjustment is I'm not sure about.
That should depend on the density ratio, I guess. Yes. Yeah. Okay. Any last question? People on Zoom. Any last question? If not, let's thank the speaker again.